My name is Renee Weber from NASA's Marshall Space Flight Center in Huntsville, Alabama. And we are having some Alabama weather today. So if I suddenly disappear, I apologize in advance. There has been some pretty strong winds and the lights have flickered a couple of times and the kids were let out from school early. And so there's also a distinct possibility that they'll be barging in and bothering me at some point. So again, apologize for any interruptions. But I'm here today to talk to you about the Lunar Geophysical Network mission. I am currently serving as the Deputy PI under our fearless leader, Clive Neal. And if you're not a diehard fan of the Lunar Geophysical Network mission, that's okay. I hope I will convert you. But if you are, I'm sad to report I don't have a ton of new information in this presentation. But what I have done is pulled together a lot of material from presentations that have been made publicly in other venues in the past year or so, and try to pull together a coherent story that tells the story of the mission. So at the dawn of the age of planetary exploration, seismology was considered a key technique for understanding a planet and its interior. And seismometers were among the first instruments sent to other planets, both to the moon and also to Mars with the Viking missions. And in this picture here, we see Buzz Aldrin with the Apollo 11 seismic experiment. So you can see the solar panels that have been deployed, and you can see the antenna in the middle that's pointed back at Earth. And then just beyond that, you can see the laser retroreflector, which was another geophysical instrument that had taken to the moon in the very early era of human exploration. And these instruments really laid the groundwork for the first long-lived extraterrestrial geophysical network. So the Apollo missions revolutionized our understanding of the lunar interior, but there are still a lot of questions remaining regarding the detailed global structure of the moon's deep interior. And this has bearing on the moon's thermal, petrological, and rotational history. So geophysics is the primary way that we look at the interiors of planets. And interior properties provide constraints on formation and evolution models, and also provide possible indicators of early dynamo for magnetic field generation. And the terrestrial planets all share this common structural framework, a crust, a mantle, and a core, which is developed very shortly after formation and which determines a body's subsequent evolution. And so much of the Earth's early structural evidence has been destroyed by plate tectonics. So these so-called ancient planets, which includes the moon, retain more information about their early interior structure and therefore represent ideal bodies to explore to advance our understanding of all terrestrial planet formation and evolution. On the moon, the heat engine that drove this initial differentiation waned after the first 1.5 billion years of lunar history, as the volume of magmatism decreased dramatically. So therefore, the moon in particular represents an end member in terrestrial planet evolution, as it potentially preserves that initial differentiation stage up through a magma ocean. And so the structure and the composition of the moon's interior specifically provides fundamental information on the initial evolution of any differentiated terrestrial planetary body. And so the overall point that I'm trying to make here is that lunar science is essentially solar system science when it comes to terrestrial planets. So I'm going to go through some of the geophysical measurements that have been made in the past one by one, and then talk about how Lunar Geophysical Network will build upon these. So the first is monitoring of the moon's geodetic parameters. So to first order, the moment of inertia of the moon is roughly approximated by a homogeneous sphere. And so we know that if a core is present, it has to be pretty small. Of course, we know that the real moon is much more complex than a homogeneous sphere, and we've observed these hemispherical dichotomies in the crustal thickness, in the presence of volcanism, the presence of magnetism, and also in the distribution of heat-producing elements. And so there's also the question of how these dichotomies, or whether and how these dichotomies propagate into the interior. Lunar laser ranging has been precisely monitoring the moon's geodetic parameters since 1969, using those retroreflector arrays that I mentioned earlier, deployed during both the Russian, the Apollo missions and the Russian Luna missions. So Luna 17, also called Lunokhod 1, was just recently integrated into the Apollo Lunar Laser Ranging Network in 2010, thanks to LROC finding its location on the surface and being able to give accurate coordinates that we could range to with Earth-based lasers. So changes in the round trip laser travel time is what provides information on the rotation of the moon, which can be analyzed to separate out lunar orbital motion from actual geodynamic effects that depend on the internal structure. So lunar laser ranging, in addition, also allows for fundamental astrophysics research to be conducted from the moon, looking at things like the general theory of relativity, the inverse square law, testing the equivalence principle with these very, very accurate laser ranges. So going back to the sort of understanding geodynamic effects, dissipation measured by lunar laser ranging provided that first evidence for a fluid core in the moon with a radius dependent upon the assumed composition. But right now, lunar laser ranging still can't constrain an inner core, in part because of the restricted geographical extent of the existing laser retroreflector array or network. So that limits the accuracy of lunar rotation and tide determinations. So for lunar magnetic induction, there was electromagnetic sounding of the moon performed both during and after the Apollo program that provided broad constraints on the size of the core, the composition of the mantle, and the interior temperature structure overall. Electrical conductivity and mantle temperatures were constrained at single points at the Apollo stations, using concurrent surface and orbital magnetometer measurements. So on the left there, I have a picture of one of the Apollo lunar surface magnetometers. These measurements observed lateral heterogeneity in electrical conductivity, which is consistent with the presence of the PKT. And also the lunar prospector and Kaguya magnetometers detected an induced moment within the moon, observed when the moon was in the Earth's geomagnetic tail. And assuming that this induced field is caused entirely by electrical currents, near the surface of a highly electrically conducting metallic core, you can also back out a preferred core radius from those measurements. But I do point out that it is not, a core in that case is not required to fit the observations. So there's still some limitations there in terms of constraining the deep interior structure. So for seismic measurements, a passive seismic experiment was deployed on the lunar near side at multiple Apollo sites. So that's the yellow triangle in the figure on the left. That network operated continuously from 1969 to 1977, and it detected many different types of naturally occurring seismicity, deep moonquakes, shallow moonquakes, meteorite impacts, also the artificial impacts, which were expended spacecraft parts that were intentionally crashed into the lunar surface, both to calibrate the seismometers and to constrain shallow structures, similar to how we do active source seismology on Earth. So these measurements, so if you look at this figure here, this is essentially like a cross section of the moon with the near side on the upper half. So, point up, I got a point over here. Up is going towards Earth and down is the far side. So this is the near side, and all of the seismic stations, obviously because the Apollo missions only went to the near side, that's where the seismometers were. And so these stations didn't really observe any seismic energy that originated from the far side, from within this region here, D, essentially. And so there's sort of two different conclusions that you could draw from that. One, the far side is aseismic, which we think is pretty unlikely, although given the other hemispherical dichotomies that are known to exist on the moon, wouldn't be a complete surprise if that turned out to be the case, but probably pretty unlikely just given how we've observed other types of seismic activity, with a pretty broad distribution across the near side. The other interpretation is that there's a core there that attenuates seismic energy originating from the far side, sort of like the shadow zone on the Earth. And so the deepest moonquake source regions that were estimated from the Apollo data is between 1,200 and 1,400 kilometers depth. So you can also infer a core radius from those measurements, but that's a moderately uncertain estimate. To go into a little bit more detail about the seismic measurements, that is my area of specialty. I'll talk a little bit about seismic scattering and what the limitations of the Apollo seismic data were. So the lunar regolith strongly scatters seismic energy. So lunar seismograms are of limited quality when compared to their modern terrestrial counterparts. So on the left here, the top three waveforms are lunar events, lunar seismic events. The top one being sort of a high quality, the middle one being sort of a mid quality, and the bottom one being sort of a low quality. And then the last one here representing a stack of moonquakes, which is essentially, taking advantage of some of the characteristics of deep moonquakes to enhance signal to noise. And so you can see that, and then this bottom one is a terrestrial seismogram. And so you can see, on the terrestrial one, you have the first arrival, and then you have all of these secondary arrivals that represent different ray paths through the Earth. And you can't really see any of that on the lunar seismogram. You see the first arrival, and then you just see a really ringy coda. So any type of secondary phase that contains information on the deep structure are masked by that coda. And those phases essentially represent reflections of seismic energy from major layer boundaries within the moon, like the crust mantle boundary or the core mantle boundary. And so, if you're familiar with terrestrial seismology at all, this is a ray path figure that shows both the direct phases, which are the first to arrive, and then the phases that interact with the core, either by bouncing off of it or by being transmitted through it. Those are the ones that come later in the seismogram. And so we just don't really see those in the case of lunar seismograms. And so as a result, a lot of the structure models that were derived from these seismic measurements have uncertainties that are reflected in them. Crustal thickness estimates have actually decreased over the years as newer and more computationally expensive techniques have been applied to the data. Early models that were based on arrival time inversion alone have since been supplanted by newer models that use things like maximum likelihood estimates or joint seismic and gravity inversion, pre-Grail gravity inversion, I'll point out, and also free oscillations. And the newer models mostly agree that the only major discernible discontinuity in the deep interior or in the interior is the crust mantle boundary, which is located around 30 kilometers deep. And there's not really any consensus among models regarding the presence of a mid-mantle seismic discontinuity. In the past, this has been used to suggest the lower bound of an ancient magma ocean, And so that's not something that we really see, especially in the later models, which essentially suggest that all the way down to the core, velocities and densities are constant. So that brings us to recent advances in lunar geophysics. So I mentioned GRAIL, of course. The GRAIL gravity mission mapped the moon's gravity field in extreme detail. GRAIL crustal structure is very, very tightly constrained, but still tied to these uncertain ground truth seismic estimates that were made at the Apollo landing sites. So this really sets up the Lunar Geophysical Network mission to dramatically enhance one of the highest fidelity planetary data sets that we have. So recent reanalysis, well, it's not so recent anymore. Within the past decade, reanalyses of Apollo seismic data have found evidence for core reflections that I mentioned earlier were very difficult to see. So those studies both include and don't include the presence of a partial melt layer just above the liquid outer core. So GRAIL mission in particular produced a family of core models that are consistent with geodetic parameters and with seismic constraints, but offer different perspectives on whether this partial melt layer is really required to satisfy the available constraints. So a melt layer is consistent with inversions of multiple geophysical data in combination with other observations like phase equilibrium computations, but maybe not required in things like viscoelastic dissipation models. And those are based on laboratory experiments of mantle materials. So the existence of a partial melt layer would also inhibit core cooling. So that brings us to synergies with geothermal measurements. So geothermal measurements track heat production in the interior and the temperature distribution in the interior. Apollo had heat flow experiments, but they were both within or near the boundaries of areas that were dominated by thorium-rich crust. And how that PKT came to exist actually depends on the internal structure. Geophysical data provide context for thermal emission and for volcanism studies. They also reveal the evolution of the lunar dynamo, by which the moon may have generated and maintained its own magnetic field. So looking at synergies with paleomagnetic measurements, magnetism is ubiquitous in the solar system. Both the deep structure and magnetism have bearing on the lunar dynamo, which in turn has implications for lunar thermal history and for the state of the core. We don't know the full nature of the extinct lunar dynamo, and to some extent it's surprising that it even existed on such a small body as the moon. We can constrain dynamo history with paleomagnetism and also via crustal magnetism studies, but we don't know the exact origin of the magnetic anomalies or things like swirls. And recent modeling shows dynamo mechanisms that use core convection can't achieve a lunar dynamo that meets the observed paleomagnitude and duration. The dynamo would run out of energy, so there would have to maybe be like some other kind of secondary dynamo mechanism to explain paleo intensity observation. So there's still some work to be done here as well. So how can we develop an internal structure model for the moon that is consistent with all of the observations and provides logical context for the moon's early history? There are complex internal processes that drive the distribution of surface observables. So if the PKT, for example, is indicative of thermal upwelling and mantle overturn, a potentially partially molten region could act as a thermochemical blanket that prevents the core from cooling. I think I mentioned that earlier. But anyway, in the past 50 years, we've learned a ton about the moon, but there are still a lot of open questions that could be addressed by a future lunar geophysical network. And so, Apollo's legacy was really an evolution in our understanding of the moon. And to build upon that legacy, The current planetary decadal survey and hopefully the next planetary decadal survey recommends a lunar geophysical network as a prioritized mission. So that would be a network of at least 4 nodes, each consisting of a seismometer, a heat flow probe, a retroreflector, and a magnetometer, operating continuously for at least 6 years, but preferably 10. That would enable progress towards a consistent model of the moon's interior from the crust to the core. So our team, the Lunar Geophysical Network mission team, recently completed a NASA-funded planetary mission concept study and is currently in formulation for New Frontiers 5. And I'll talk about that more in a minute. So going back to our outstanding questions in lunar geophysics, we don't know the extent or duration of the lunar dynamo. We don't know the exact origin of the moon's crustal magnetic anomalies. We don't have unambiguous observations of a mid-mantle discontinuity, a partial melt layer above the outer core, or the nature of the inner core. We don't know how surface hemispherical dichotomies propagate into the interior. And in fact, we don't even understand how or why moonquakes occur. So deep moonquakes, if you look at the pressure and temperature regime of the moon, are technically occurring in a region that should be dominated by ductile flow rather than brittle failure. And recent work has also suggested for shallow moonquakes that they could be related to lobate scarp slip. So there's a lot of questions that a lunar geophysical network could still help explain. Stepping back further to look at big picture questions, there are several terrestrial planetary hypotheses that can be tested with new geophysical data from the moon, looking at how solar systems form and how they evolve over time and when major solar system events happened. The moon records the entire history of the early solar system. Looking at how terrestrial planets form and differentiate. Parts of the moon preserve remnants of magma ocean crystallization, which presumably took place in the early histories of all terrestrial planets. So following the crystallization of the magma ocean, was there an overturn event? Is the crustal PKT layer the origin of the partial melt layer at the core mantle boundary? Crustal thickness, lateral variations in properties, the mantle, especially the lower mantle, these all provide insight into processes like this. Understanding processes that shape planetary surfaces and how the surfaces record solar system history. So for the moon and other smaller bodies, stagnant lid conduction is assumed to be the norm, as is global contraction. So this is going back to thermal evolution and how it's tied to tectonic evolution and the rate of heat loss, all linked to interior structure and dynamics. Even questions like looking at how worlds become habitable and how habitability is sustained, and also looking at hazards in the solar system for human exploration. So seismology in particular can assess the risk from seismic shaking, which is definitely needed as we push towards a sustained human presence on the moon. So in the past decade, lunar science has made multiple advancements in our understanding of the moon's interior, building from Apollo's geophysical legacy. These are some key relevant points from a 2018 League Special Action Team called Advancing Science of the Moon, which was chartered to reevaluate the SCAM report. And so I won't read through these, but when taking into account advancements from the GRAIL mission, from improved analyses and also modeling techniques from paleomagnetic sample analyses, it's very clear that a more nuanced view of the lunar interior drives these new questions that can be answered by a lunar geophysical network type mission. There have also been technologic advancements in geophysical instruments themselves. We've recently seen through the success of the Mars InSight mission, particularly through the development of this very broad band seismometer, which is, essentially the most sensitive seismometer that's ever been built. InSight marked the first placement of a seismometer on the surface of a planetary body since the Apollo and Viking era, revealed the discovery of Mars quakes, characterization of the seismicity of Mars, and the first direct constraints on the internal structure of Mars. So we're very hopeful to continue applying such advancements to other planets. So Lunar Geophysical Network will, of course, leverage InSight's advancements in instrumentation and methodology. And in addition, there are multiple instrument development efforts underway for both Lunar Geophysical Network and for CLPS landers. So this is a list of the US-based seismometer development efforts that I'm aware of, many of which are currently undergoing lab and field tests. And I'm sure, in fact, that this slide is probably out of date and there are more on here that need to be populated. Since we have such a strong focus on lunar science, in part thanks to the agency's Artemis program, I hope to see this list grow. So for heat flow, we now have heat flow instruments deployable from small robotic landers, much more robust in its ability to penetrate the regolith than the mole-based system that was used for the InSight mission and unfortunately failed. It uses a jet of compressed gas that lofts regolith out of essentially a borehole that opens as the probe descends. So this particular instrument, which is called LISTER, the Lunar Instrumentation for Subsurface Thermal Exploration with Rapidity, has been selected to fly on a CLPS lander. For electromagnetic sounding, so magnetotelluric sounding has been used on Earth for more than 50 years and provides sounding from a single surface station without any knowledge of the source field. So it doesn't require a concurrent measurement made from orbit. So there is also a CLPS payload called the Lunar Magnetotelluric Sounder, which combines this flux gate magnetometer with these ballistically launched electrodes that go out in orthogonal directions, create this essentially an antenna to help do this sounding. So we'll also fly on a CLPS mission in 2022. And then lastly, we have lunar laser ranging. So new laser retroreflectors are also scheduled to fly on CLPS landers and will support a factor of 100 better range accuracy and factor of 100 better science parameter uncertainty. So there is actual payload called the Next Generation Lunar Retroreflector. But I'm also pretty sure that NASA has made an agreement to send a retroreflector on every single CLPS lander. So these are all the CLPS deliveries that are planned between now and 2025. And I've put green check marks next to the ones that contain geophysical instruments. So 3 of them on this Firefly lander and the Farside Seismic Suite, which was part of the first class of PRISM selections. Provider still TBD, I think, will fly to the moon within the next few years. So I wanted to briefly mention CLPS, Artemis, and the bearings that these programs have on Lunar Geophysical Network. The CLPS landers currently carry between 30 and 50 kilograms of total payload and only last for 1 lunar day. The Lunar Geophysical Network concept, which I'm about to get into, requires a long-lived integrated science mission. So right now, CLPS missions can enable the Lunar Geophysical Network by retiring key risks. So looking at things like instrument deployment strategy, characterizing the noise of the lander itself, and improving thermal and power performance, with the hope that CLPS can evolve towards longer-lived surface missions. So multiple new lander providers may eventually enable a mission like the Lunar Geophysical Network to shop around and save on mission bus costs. I also wanted to specifically mention, within human exploration, the Artemis program obviously very focused on returning humans to the moon. But landing at a single site will not help fulfill the Lunar Geophysical Network's goal, right? The goal of deploying a network, which requires being at multiple sites on the moon. But if there are opportunities to deploy a long-lived geophysical node at the human base camp, this would be very enabling for broader Lunar Geophysical Network coverage. So now I'm going to talk a little bit about the planetary mission concept study that I mentioned earlier. So many of the instrument providers, or really all of the instrument providers that I talked about on those CLPS landers, are part of the LGN team. They contributed material to this presentation, and they contributed to our concept study. So this was finished in 2020, and I put a link to where you can find the document if you're interested in going and reading about it in gory detail. But the planetary mission concept study was specific to look at outstanding questions in lunar geophysics, which have broad relevance across planetary science. And our team consists of lunar scientists and instrument developers that have been backing LGN for decades, and includes members from both Apollo and InSight missions. So the science overview of the Lunar Geophysical Network mission itself, the goal is to understand the initial stages of terrestrial planet evolution. And we do that through four major objectives: defining the interior structure of the moon, constraining the interior and bulk composition of the moon, delineating both vertical and lateral heterogeneities within the interior of the moon as they relate to surface features and terrains, and evaluating the current seismotectonic activity of the moon. So to go from objectives down to investigations, we want to determine the size, state, and composition of the core. We want to determine the state and as well as the chemical and physical stratification in the mantle. We want to determine the thickness of the crust and its vertical and lateral variability. I'm starting to get tongue-tied. We want to determine the thermal state of the lunar interior and look at the workings of the planetary heat engine. And of course, monitor impacts on the surface, both for the benefit that they provide to constraining internal structure by serving as a seismic source, but also as an aid to protecting astronauts. So those are our secondary science objectives. Oh, these are all click through. I didn't realize that. Characterizing present day impact flux on the moon. So the picture there at the top, this is impact flashes that are recorded using ground-based telescopes on Earth. So helping to characterize the present impact flux is something we can do with LGN. Also obtaining fundamental information about moon and moon plasma interactions, solar wind. For exploration, I already mentioned documenting and locating shallow moonquakes and meteoroid impacts, which pose hazard to humans. And then we have some Earth-based support facilities, which include the lasers that range to the retroreflectors, and then the telescopes that monitor for impact flashes. So the high-level mission concept is to deploy 4 identical landers globally, deployed around the moon, to live for a long time, so a 6-year minimum with a goal of 10. This allows for other nodes to be added, which helps strengthen the science return. So this harkens back to the International Lunar Network, which was a NASA concept that was done during Constellation era. And the mission has to fit within the sort of rules of the New Frontiers paradigm, has 4 landers that are all launched together and deployed sequentially. So that's the baseline mission. The threshold mission is 2 landers deployed at sites 1 and 2 here. I don't know how well you can see these numbers. I have a better plot that shows landing sites. I'll talk about that more later. In distinctly different terrains. We nixed the far side lander in that case, but we still cite them such that we hope to be able to record seismicity from the few far side sources that we know are active, which helps us constrain the core structure. Still allows us to expand the lunar laser ranging network. And of course, we can still do our heat flow and our electromagnetic studies. So the parent spacecraft, in this case, we looked at different ways of doing this in the concept study, whether the bus itself remains in orbit as some kind of comm relay, or if there's a separate comm relay satellite that also launches co-manifested with the landers. In either case, we need a comm relay for the lander that's on the far side. And each lander is also able to send data direct back to Earth, so that comm relay can act as sort of a backup communication mode for the landers that are on the near side. It also helps with deployment in the event of non-nominal landing. So this is just the LGN payload component. I won't go through this in detail, but we have our seismometer, our heat flow probe, our laser retroreflector, and our magnetotelluric sounding suite. We also looked at different types of instrument deployment, whether we wanted to have a VBB that sits on the ground, similar to InSight, or whether we wanted to have a short period instrument that's actually buried, which eliminates a lot of thermal variability, but increases deployment complexity. So our lander concept, this is again just from our concept study. And I don't know if I mentioned this, I'm sure it was on the slide. We did our concept study with Goddard Space Flight Center's Mission Design Lab. So in this photo here, you see the very broadband seismometer, which sits in the shadow of the lander. This helps provide a more stable thermal environment. The heat flow probe, which is deployed from the leg of the lander, the retroreflector, which is deployed from the leg of the lander, and then the magnetotelluric sounder, which has these little ballistic ejection mechanisms to send the probes out orthogonally from three sides of the lander. This is a look at our mission architecture. In the study, we assumed a Falcon 9 heavy fairing. So this is the stack with the orbiter at the bottom, the comm relay, which in our case, we were able to host a low mass boom with a magnetometer as sort of an additional science measurement. Key driving requirements for the mission. It's a Class B mission with a 6-year mission life, goal of 10 years. I mentioned already that threshold mission has only 2 landers, with both of them being on the near side, so therefore no comm orbiter is required. A 0.5 meter of ground clearance, that comm asset, whether or not it is the actual deployment spacecraft itself or a separate independent comm relay. Underbody, any instruments that are mounted underneath have to be protected from the thrusters and the plume that comes up during landing itself. So we looked at different ways of doing that. Also looking at surrounding the seismometer with some kind of curtain for thermal control. InSight has the wind and thermal shield. So on the moon, we don't have wind to contend with, but thermal control is still something that we're concerned about, especially with the large day to night temperature variation on the moon. Our landing constraints, the retroreflectors have to be gimbaled and point to the Earth within 1 degree. Any fixed cameras on the lander can't be blinded by the sun. We have to avoid large rocks and be able to handle a 10% grade. And then we did point out one thing about day and night operations. So, we don't have the ability to hibernate at night. Seismic network needs to be recording continuously. But we did permit operations to look different during the night, since power and thermal becomes a much tougher job. So we record data continuously, and then we look at different ways to telemetry the data back during daylight hours. So our mission overview, we have 4 landers that permit global distribution. including the far side, and also allows for redundancy. So they are deployed sequentially. So we can decide on the fly if in the unfortunate event that a lander does not land nominally, we can redeploy one of the other landers back to its site if we decide that that site is higher priority. We need a long-lived mission to maximize the science and potentially allow for other nodes to be added either by international partners, commercial partners, or human exploration missions during the lifetime of the mission. So this increases both the fidelity and the value of the data obtained. I think I've talked about all of the rest of this. Each lander is also able to send data directly back to Earth. So we have a comm backup. And this little graphic just kind of shows the different phases from launch to cruise, orbit insertion, that we go into a low circular orbit for deployment and release all of the landers over the course of one lunar day. And then once the landers land, then we go through instrument deployment and commissioning and checkout and all that, and then we go into operations. So I'm going to wrap up by talking about our landing sites. The landing sites were chosen very carefully to address some of those, Apollo limitations that I mentioned earlier. So, discrepancies in the size and the nature of the core, the mantle, the crust. We had heat flow from Apollo only at 2 locations, both close to the boundary of the PKT. And then we now know that those have different crustal signatures. So we wanted to make sure that our heat flow measurements were both, firmly within the PKT and then firmly outside of the PKT. So we don't have any of these boundary effects. Magnetometers were deployed at 3 sites during Apollo, but they weren't networked. So we, and Apollo 12 in particular did those joint measurements with Explorer 35 satellite. So they were doing low frequency electromagnetic sounding, but only in the PKT. So again, global sites allow for more thorough science investigation. The passive seismic network. So here we have the little triangles are the Apollo sites. And you can see it was pretty narrow aperture triangular array focused on the near side. So we've greatly expanded the footprint of the seismic network, put a lander on the far side so that we can get global crustal structure, we can get better constraints on deep structure, and we can resolve the core. Similarly for retroreflectors, the best way to improve the fidelity of the existing laser ranging data set is to put your landers as close to the lunar limbs as you possibly can. And so we're also greatly expanding the footprint of the retroreflector array. I can't stress enough the importance of sending a lander to the far side. We have 0 geophysical data from the far side of the moon in situ. So, we'll be doing a first here. So I think that's it. In conclusion, I want to reiterate again, lunar science is solar system science, and understanding the moon structure, and using that to sort of story tell its early differentiation and subsequent evolution helps us understand that process for all terrestrial planets. I will point out, we do have a lot of community support for LGN. I already mentioned that it was named as a priority New Frontiers mission in the current planetary decadal. We do have a letter from CAPS stating that they intend to carry it forward in the 5th New Frontiers announcement of opportunity. And so in just a few short weeks, we'll know for sure. LGN is also endorsed by League. And we take that endorsement we're very happy and hope to be able to fulfill these community desirements for the science that LGN can enable. And lastly, I can't help but point out, the moon is NASA's current exploration focus, and the LGN mission in particular helps constrain seismic risks for moonquakes and impacts. And so it's very synergistic with the goals of the human exploration program. So I hope that I have helped make you all a little bit more excited about LGN, and I'm happy to take any questions that you might have.
Thank you, Renee. This is Lisa. Great to see you. Great
Hi,
talk.
Laura. Thank you.
Yeah, I think this is very exciting. I think you're going to have a great deal of focus on this as you move forward. Let's see, do we have any questions? And if so, please put them in the chat. Let's see, Renee, did you talk about, and I missed the first part of your talk, I apologize, we had a management discussion at lunchtime that ran over. Did you talk about the Schrodinger prism experiment? Are you involved in that?
Yes, the far side seismic suite.
Yeah, there you go.
Yes, so I'll go back to the CLPS chart. Yeah, far side seismic suite is one of the CLPS payloads that is, we're sort of considering it like a risk buy down for LGN because it helps our instruments get to TRL9. And it's a little bit different from some of the other CLPS missions because it has this longevity component. So the far side seismic suite payload is trying to be independent of the lander, right? So all of the other CLPS missions so far, or CLPS payloads so far, kind of depend on the lander for power and comm. And so when the lander dies, the science dies.
Okay.
So far side seismic suite is taking a step beyond that to be its own independent power and communication platform. So that gets us a little bit longer, but still, not really approaching the longevity needed for a lunar geophysical network mission.
Right. Gotcha.
Power, thermal, and comm are all very, very challenging.
Yes.
One of the big differences between lunar geophysical network and the Apollo geophysical instruments, or ALSEP, was that ALSEP had a radioisotope thermal generator to supply power, and so you basically had this unlimited supply of power that could keep you alive, keep you warm. You didn't have to worry about it. But that so far is, we think, pretty unlikely that LGN would be able to convince NASA to give us all of the currently available MMRTGs.
Right.
But that is something that we looked at in our concept study.
We do have some more questions from your audience. From Alan Treeman. He has questions about placement of the network elements. Why in Korolev crater rather than on the more representative highlands? Yeah,
so Korolev crater was chosen for a couple of reasons. It's kind of hard to see on this figure, but the green dots are locations of lobate scarps. And then the cyan dots are what's the word? For, the point that is exactly opposite the antipode of the known distribution of deep moonquakes. So, as I stated, one of the goals of the seismic instrument is to try to capture these core traversing phases. And so I didn't put a ray diagram in here, but if you are at the antipode of a source, then you have the potential to record the transmission of energy through the core. And so the Korolev Basin, and I know it's hard to see the dots, but there is a high concentration of deep moonquake cluster antipodes, including some of the most active clusters on the near side.
Okay, excellent. From John Panuto, Artemis is not a network solution, but is there any synergy there at all?
Yeah, I mean, definitely. The goal is to get as many seismometers on the moon as possible. And I would absolutely be ecstatic if there were Artemis seismometers, CLPS seismometers, and Lunar Geophysical Network seismometers all operating at the same time. The science only gets better as the number of stations goes up. And, if you look at terrestrial, how many, we have permanently installed, hundreds of permanently installed seismometers that operate on the Earth. including like at the bottom of the ocean. And so, my goal is to get to that level of fidelity on the moon.
Excellent. From Tom Sutliff, you touched on this earlier, but was there a hard constraint to go solar versus the ALSEPs being RPS powered to enable the long life capability?
Yeah, so I mentioned that. There's sort of two factors at play here. One is just the availability of radioisotope sources. Like NASA just doesn't have that many. And since this is a competed mission, we are competing with missions like to the outer solar system, and possibly even like places that we've never gone before. And so, whereas one MMRTG might be able to enable a mission to, Uranus and Neptune, we would need all 4 MMRTGs for one mission. So it's just challenging in a competitive environment. The other challenge is, we are looking at the potential of working with, the CLPS program. NASA has this entirely new paradigm for delivery of payloads to the lunar surface. And we don't know yet whether or not that paradigm will be mature enough to work for LGN, but it's obviously something that we're looking into. And there are sort of legal ramifications for flying radioisotopes on a commercially developed mission.
Very good point.
Interesting challenges.
Yes. So James Salmon asks, I understand the crushing of the regolith during Apollo's seismic measurements severely compromised the measurements themselves. Do you expect this to be a problem?
So the regolith is always going to be an issue. We have looked into the extent to which potentially burying an instrument can mitigate some of the effects of scattering. But the reality is that you have to go down to like definitely the multi-kilometer scale before you reach intact lunar crust. So there's always going to be a certain amount of scattering that you just can't deal with. But improvements in instrumentation over Apollo, as well as improvements in data processing, are 2 ways that we can definitely mitigate what we anticipate in terms of scattering.
Let's see another question from Alan Treeman. How will the current network sites allow investigation of SPA's structure?
Yeah, that's a good question too. One of the ways that we do that seismically is by looking at the, ray paths that are traversed by the seismic sources, either the ones that we already know about thanks to Apollo or new ones that we don't know about yet. And that's where that far side site in particular becomes valuable, because you increase the density of rays traversing any given region, including SPA.
Great, thank you. Let's see, here's another one. Great. John Littleton, apologies if you've covered this. How does thorium in the Apollo landing sites interfere with seismic instruments?
So I don't think it would really interfere with the seismic measurement that much, other than it being a factor to, if there's a structural ramification of the presence of thorium, then we hope the seismometer would help constrain that.
Okay. And let's see, I don't see additional questions. Last chance, everyone. Any other questions? It looks like not, Renee. Thank you so much for talking to us. It's great to see you today. And will we see you in Houston, do you think?
Yes, in fact, I just booked my travel.
Oh, excellent. Outstanding. That's great to hear. Thank you.
We'll
look forward to talking to you then.
Thank you.
Absolutely. Thank you for having me.
You're most welcome. It's our pleasure. And we'll talk to you soon.